Just to the west of the new city of Flagstaff, Arizona, beneath a starry sky, stands of ponderosa pines marching off into the distance. There, enshrined in a domed observatory atop the peak of a modest mesa, despite the lateness of the hour, a solitary figure works, surrounded by some of the finest astronomical equipment of his age, watched over by the silent trees. The year is 1900. That man is Percival Lowell, and he is studying Mars. A wealthy American businessman, Lowell established this observatory in order to pursue his singular, all-consuming passion, the study of the red planet. The observatory and the 24-inch telescope it houses is the first in the world to be sighted at altitude. On top of Mars Hill, as it will come to be known, Lowell's telescope is more than 2,000 meters above sea level, enjoying the benefits of an extraordinarily clear view of the heavens. With less atmosphere to distort the light on its way to Earth's surface, the new observatory reveals stars and planets with remarkable clarity. So, Lowell sits in the observing chair. Colossal telescope to one eye, notebook in his lap. And in this age, long before the first accurate photographs of the planets, oh, what riches can he see? Great waterways, singular and doubled up, crisscrossing the Martian landscape. Joined by oases, great pools of water like reservoirs. And he sees vegetation along the canals, vegetation that waxes and wanes with the passing of the seasons. What could be the explanation for this complex terrain? Surely this isn't something that could arise from natural forces alone. Very much a man of his time, living in an age of empire, industry and railways, Lowell concludes that the only rational explanation for what he sees is intelligent minds executing vast civil engineering projects. These Martians must be highly advanced, he reasons, but desperate. Their planet is drying out, losing its water. So they have no choice but to channel it from the polar ice caps to their towns and farmlands at lower latitudes. What terrible misfortune that Mars was dying. The Martians going to such great lengths to survive. Lowell's work was evocative, sparking the public's imagination as well as the likes of H.G. Wells of War of the Worlds fame. But it also attracted criticism. No other scientists could see what Lowell was seeing. They didn't see his canals or his oases or the summer bloom. Perhaps it was because the new observatory revealed closely held secrets no others could see. Or perhaps Percival Lowell was carried away with wishful thinking. At the time, it was impossible to know for sure, and the imaginative public would have to wait nearly 70 years to know if the Martians and their canals really did exist. The answer finally came in the 1960s, with the first unmanned missions to Mars. Robotic probes dispatched by NASA, known as the Mariner missions. Orbiting the red planet, these first travelers to another world captured the first close-up images of the surface. Those images, grainy and indistinct, showed a rugged, cratered surface. There was no trace of water, but no trace of Lowell's canals either. With subsequent orbiting missions and eventually landers and rovers too, Mars's history has gradually given up its secrets. There never was an ancient civilization of Martians here, and it's been a very, very long time since there was any water. Yet, at some point in the near unfathomable depths of time, water there was. At the same time as Mariner offered up new perspectives on Mars, another space mission provided brand new perspectives on our world. In December 1972, as Apollo 17 made its way to the Moon for the final lunar landing of the space race, one of the astronauts on board turned his camera to the Earth. Home to every human who has ever lived, every story that was ever told. The image he captured, known as the Blue Marble, has since become an icon of unity and, of course, fragility. When seen from space, our world is spectacularly blue, adorned with delicate wisps and whirls of cloud, graceful ice caps, and frosted flows. Compared to dry, dusty, red Mars, our planet couldn't be more different. A lush, ocean world brimming with water in all its guises. But how did the two worlds end up so different? What became of the oceans of Mars? And where did our water come from? Whirling through space at about 150 million kilometers away from our Sun, the Earth is the only planet in our solar system with abundant water. More than 70% of its surface is covered with ocean, in places plunging 10 kilometers deep. There's enough water in our oceans to fill 550 trillion Olympic swimming pools. But there's also water in rivers and in lakes that trace delicate, sinuous patterns all across the land surface. Underground aquifers contain fresh groundwater that can penetrate the rock up to 2 kilometers down. Not to mention the many millions of cubic kilometers locked away in ice sheets, glaciers, and bergs. And water is in the atmosphere too. As a gas, it's a small but significant part of the blanket coating our sphere, creating humidity, the sticky closeness of a hot tropical evening. At higher altitudes, it exists as a liquid, tiny droplets suspended by rising air currents. Clouds. And higher still, the clouds freeze to ice, ready to begin their descent back to the surface. Our world is ruled by water, its evolution guided by it. Our water is the lubricant that keeps plate tectonics going, keeps the rocks recycling. Our water is the reason life has flourished here for billions of years. Our water is what defines our Earth. But the story of how water got here in the first place is far from straightforward. It's a mystery concealed by the depths of time, only now in the 21st century being revealed by cutting-edge new research. When the Earth formed 4.54 billion years ago, it did so in a region of space lacking the ingredients to forge life-giving water. The newborn sun was powerful enough to strip the inner parts of the protoplanetary disk clean of hydrogen, the lightweight element that makes up 2/3 of a water molecule. Without hydrogen, there could be no water. So, all of the planets of the inner solar system were born dry, barren rocks. Perhaps some water could have escaped the young sun's relentless gale if it hitched a ride bound chemically to particles of dust. When the dust began to cling together into swelling planetary embryos, the water was trapped within, still bound to the rocks inside these planets. Only after millions of years of grinding plate tectonics and overturning, bringing these inner rocks to the planet's surface, could that water be released. But could a trillion liters of water really be locked away inside a planet during its formation? Maybe some of the Earth's water dates to its earliest days, but scientists don't think this is the whole story. Instead, they look to altogether more alien sources. For while the inner solar system was swept clean of water, the outer reaches were awash with it. There, further away from the sun, temperatures were cool enough for hydrogen to combine with oxygen and condense, then freeze into icy crystals. Each ice crystal is tiny, but beyond the so-called snow line of our solar system, space is awash with frozen water, locked up inside asteroids, comets, even inside the giants, Neptune and Uranus. But these water-rich bodies are enormously distant. They're more than 4 times the distance between our world and the sun. A vast gulf of space opening up between the young, dry Earth and this remote, interplanetary reservoir. It would take a planetary turmoil for their paths to cross over the distance. Luckily for the Earth, planetary turmoil is exactly what the early solar system looks like. Giant gas worlds like Jupiter and Saturn form and jostle for a stable orbit among unruly protoplanets. Gravity pulls and pushes planets into new orbits, flinging smaller objects across the solar system. As Jupiter moves first towards and then away from the Sun, it passes through icy bodies at the snow line, throwing them into a tumult. Some are ejected from the solar system entirely, launched on million-year journeys to parts unknown. Others are flung inwards, towards the inner reaches of the solar system, towards the Earth. Many miss, of course, but enough are drawn in by the Earth's gravity, pulled onto an inescapable collision course. When they hit, the incredible heat and force of the impacts obliterate the smaller bodies. Rock is smashed to dust and ice flashes into vapor. The water vapor, eventually cooling to liquid water, belongs to Earth now. Each impact may only deliver a little water to the Earth, but together, over the span of millions of years, these icy asteroids and comets leave oceans in their wake. If even a small fraction of them struck our planet, these icy bodies could easily be the source of our endless oceans. For a long time, comets had been seen as the most likely cosmic couriers bringing water to our world. After all, compared to rocky asteroids, comets are made almost entirely of ice. It would take far fewer collisions for them to cover Earth with water. Yet, in the last few years, spacecraft have visited both comets and asteroids, providing new data that's fundamentally changed our view, concluding that it was in fact rocky asteroids that delivered most of the water to Earth and the inner solar system. The molecular fingerprint of ice from comets is completely, irreconcilably different to that of Earth's water. In this forensic study, the prime suspect left no evidence at the scene, but the molecular fingerprint of asteroid ice is a match for Earth's water. All clues point to asteroids, jostled by Jupiter in the early days of the solar system as the source of our seas. But space probes haven't solved the mystery of when this happened. Jupiter's mighty lurch back and forth through the solar system would have happened within the first 100 million years. But it could have stirred up the asteroids so badly that they lingered in the inner solar system for many more millions of years. No rocks on Earth survive from these earliest of days. Most likely, the asteroid bombardment took place after the catastrophic collision between Earth and Theia. Since that cataclysmic event would have been powerful enough to strip our planet of any atmosphere, including water, there's also good evidence of a bombardment happening after the moon's formation. One need only to look up at the moon's face today to see the clues staring back at us. Many of the craters of our eternal companion were formed during a relatively thin sliver of its early history, between around 4.1 and 3.8 billion years ago. Scientists call this cataclysmic era the Late Heavy Bombardment, and as well as cratering the moon, similar impacts on the Earth may have delivered its water too. One final clue points to our water being extraterrestrial in origin. As well as having a surface that's uniquely water-rich, the crust also contains a remarkable quantity of gold. Elements like gold don't usually stick around with rock inside planets. Rather, they go where the iron goes, torn by the pull of gravity. Usually, during the formation of a world, gold would be stripped from the crust and dragged down by gravity into the iron core. But our crust is gilded. One of the only ways this could have happened is if the gold was delivered after the core had already formed, delivered by asteroids that left a thin veneer of precious metals and precious water on the surface. While the origins of Earth's water may still be uncertain, its fate is easier to predict. Because our home planet formed at a distance from the sun that's not too hot and not too cold, astronomers call it the Goldilocks zone for this very reason. Within the Goldilocks zone, it's just right for water to exist as a liquid. Not only that, but with small fluctuations in conditions, a little thicker atmosphere, a slight tilt away from the sun, that liquid water can easily switch between its other phases. Within just 100 degrees Celsius, water can freeze solid into ice or evaporate away into tenuous vapor. 100 degrees might seem a lot to us, but between the scorching heat of stars and the frigid depths of space, it's tremendous luck that puts Earth just in the place where conditions are right for all three to exist. And it's precisely this coexistence of the three phases of water that powers our world. After the bombardment that delivered the water, physical reactions took over. Water vapor suspended in the atmosphere eventually cools and condenses, forming tiny cloud droplets. The battered Earth is now swaddled in cloud. Within these clouds, the droplets merge. Some freeze, and eventually they fall. Rain and snow fall for the first time onto Earth's rocky surface, hissing and spitting as they land on the still cooling crust. This first rainstorm may have lasted for thousands of years. Liquid water on the surface flows downhill from the summits of mountains and volcanoes to the crumpled and shattered valleys below. On its way, it gradually wears away the rock beneath. The first river channels begin to form. In the depressions, water collects, first as puddles, then ponds, and as the valleys are filled by relentless river flow, lakes begin to form. spilling over onto one another as water levels rise. The first seas and oceans are born. Slow chemical reactions begin between the new alien water and the rocks and atmosphere it encounters. Water dissolves some minerals, creates new compounds. Gradually, the compositions transform. Rainwater falling through a carbon dioxide-rich atmosphere becomes acidic. Acid rain eats away at rock. The oceans become salty. Near the poles, where the sun is low and the winter nights are long, temperatures drop below zero and water freezes solid. Snow falls instead of rain, and over thousands of years individual flakes accumulate into mighty glaciers. Perched at the peaks of mountains, the glaciers edge downhill, excruciatingly slowly, grinding rock into dust as they pass. At their feet, the ice melts back into the growing global ocean. But closer to the tropics, temperatures are much warmer, and the sun high in the sky heats the new ocean surface. The water evaporates, filling the atmosphere again with invisible vapor that rises, cools, and condenses into clouds. The cycle begins anew. From the first water to today, the molecules delivered to the Earth all those billions of years ago have stuck around, passing through land, sea, and air in a global water cycle that powers our weather and climate, shaping the landscape with intractable force. Through the water cycle, temperature ultimately controls climate and weather. Yet it's hard to know what the climate of the early Earth really was. Over its 4 billion year history, the planet has found itself gripped by ice, coating almost the entire surface. It has also been through warm phases, where no ice at all lingered at the poles. We only know about these periods from the rock record left behind, and there are no rocks from the Earth's earliest days. Astronomers think that the sun burned dimmer and cooler when it was first born, so the Earth too would have been cooler. Without its warming glow to evaporate the oceans, the water cycle slows. Less rain, fewer rivers flowing, and gradually lakes and oceans freeze. The early climate could have been a cold, frozen desert, a frigid snowball, until the sun matured, thawing it out. But that was probably not the case. After the moon-forming collision during the Hadean, volcanoes spewed gases into the skies, which accumulated, thickening into the first atmosphere. And the composition of that atmosphere was very different to today. It was rich in carbon dioxide and methane that together have a remarkable warming effect. Heat from the sun can pass in through the atmosphere, but these gases act like a blanket to stop it escaping again. So even though the early sun was weaker, Earth's atmosphere was probably a much more powerful insulator. With the warmth locked in, it could have powered a very active water cycle, leading to a steamy, tropical climate with intense, stormy weather. The weather of the Hadean may just have been as violent as the Earth's own convulsions. And yet, however violent the storms, however gripping the ice ages, Earth's water has stuck around, cycling between atmosphere, oceans and ice caps for almost 4 billion years. Some of it might be locked into rocks and subducted into the Earth during plate tectonics, but it eventually emerges when volcanoes erupt again. The relentless solar wind sweeps past the planet, threatening to blow away the atmosphere and any water vapor it contains. But the Earth's magnetic field, generated in the swirling iron core, is a shield against this erosive gale, deflecting it and keeping the atmosphere and oceans intact. Earth has kept its water all this time. But Mars was not so lucky. The same asteroid bombardment that delivered water to Earth likely did the same to Mars, just on the edge of the Goldilocks habitable zone. Though his evidence turned out to be little more than a mirage, Percival Lowell was right to conclude that Mars had suffered a water crisis. The red planet probably did have an ocean, atmosphere and weather, just like the Earth, though he couldn't have possibly fathomed how long ago this had been. Today, the two planets couldn't be any more different. While Earth sweats under a humid blanket, Mars is a silent, barren desert. The explanation for this lies beyond the reach of any telescope, deep at the center of these rocky worlds. It turns out we owe our oceans not only to the luck of our orbit, but also to the size of the planet itself. Because while the Earth was large enough, hot enough to maintain its protective magnetic field, Mars was not so lucky. It's little more than half the size of Earth, and while it may have started out with a swirling core and magnetic shield, its smaller size meant it cooled much more quickly. The core gradually froze, grinding to a halt, and the magnetic field all but disappeared. Without its protection, the solar wind battered the Martian atmosphere and surface, stripping away the gas and liquid water until all that was left was ice at the poles. That's the Mars we see today, a planet once gifted, then robbed of its water, long before any Martian civilization had the chance to evolve. Looking back to Earth, considering how much our planet has been shaped by luck and chance events, the ocean world we call home is even more wondrous. Next time, we investigate how the immense volcanic forces of plate tectonics help shape our world. And finally, we investigate how first life began to form. You've been watching the entire history of the Earth. Don't forget to like and subscribe, let us know what you think in the comments, and we'll see you next time.